Hello, this is Mr. Pruitt, and today I'm going to be talking about specific heat capacity. This is part 2 in a series about basic thermodynamics. So what is specific heat? Well, specific heat is the amount of heat or energy that is required to raise the temperature of a substance by 1 degree Celsius or 1 Kelvin. Specific heat is what we call an intrinsic property. It just means that every single substance, it doesn't matter what it is, carbon, nitrogen, aluminum, water, whatever substance you're looking at has its own specific heat. Now, all the samples of that substance are going to have the same specific heat, but each individual substance has its own. And since each individual substance has its own specific heat, it's possible to determine what an unknown substance might be by determining its specific heat. And we may do this in the lab that we're going to do on Monday. So how do we calculate specific heat? Well, specific heat may be calculated using the formula Q equals mc delta T, where Q is the amount of heat or energy that's expressed in joules. M is the mass of the substance in grams, and that's really, really important that you understand that that's in grams, because a lot of times they'll give them to you in units that have to be converted, like kilograms, or maybe they'll talk to you about milliliters or something like that, and we'll talk about in class how you do that conversion. C is the actual specific heat of the material. So if you're looking for the specific heat, you're going to be solving for C. If they give you the specific heat of the material and want you to solve for something else, solve for the other thing and substitute in the specific heat for C. And delta T is the change in temperature of the substance. Remember that delta T can be expanded to be like T2 minus T1, or the ending temperature minus the beginning temperature. So here's a problem for you. Let's say it takes 41,800 joules of thermal energy to bring 100 milliliters of water from freezing to boiling. What is the specific heat of water? All right, this part right here that says 1 milliliter equals 1 gram, that's really important. That's an important conversion for you to try to remember. I'm going to put it on the formula sheet for you as a conversion in constant, but you should probably try to memorize that one. It'll be with you through most of your science classes. So let's look at what they gave us. They told us that Q, that the heat was 41,800, and then we had 100 milliliters, which is the same thing as 100 grams of water. Now, this is what we know about water. We know that the freezing point of water is 0, and we know the boiling point is 100. So the change in temperature, or delta T, is equal to 100 minus 0, which is 100. So if we take our formula and substitute in, we can put in 41,800 equals 100 for M. We're looking for C times the change in temperature, which is 100. When we set all of this equal to each other and multiply it out, we get that the specific heat of water is 4.18. Now, the actual unit for specific heat is joules per gram degree Celsius, and I'll show you how to write that in class on Friday. So how is specific heat practical? Well, there's a couple of reasons that this is practical. The first one is the specific heat allows us to know which substances are good conductors and which ones are good insulators for heat energy. You just need to know that substances that have low specific heats can transfer heat very quickly. That means that they heat up when they cool down very quickly. Most metals have very low specific heats and very high melting points, so they're good conductors of heat. We would use them for something like a frying pan or a cake pan or something like that, because since they can heat up quickly and they can cool down quickly, and they aren't likely to melt when we put them on a heat source, they make very good. They're a good way to transfer that heat energy from the heat source to something else. Substances with high specific heats take longer to heat up and cool down. Okay, But what their advantage is that they hold their heat for much longer periods of time. So when we have a substance like water, that it takes a while to get water warm. If you start with cold water, you have to add heat to it for a good period of time, for several minutes, before it starts to get really warm. But once it is warm, it'll stay warm for a while. Remember, your skillet, once you turn the heat source off, within 3 or 4 minutes, you're able to touch that metal. But when you turn the heat source off on water, like in your bathtub, it holds on to that heat for a while. That's why you can take a bath without it immediately getting cold on you. Now, the reason that it's important that these high specific heat things hold their heat for a long period of time is that substances with high specific heat tend to be good insulators. They hold the heat in, or they keep the cold out, or they keep the heat out. All right, so a little bit more practical way of looking at this is this problem. Let's say that we have this window company and they're trying to improve energy efficiency in people's homes. And they want to develop an insulated window, like something with two panes of glass or something. And their design involves sealing an insulating gas. So they've got this gas and they're going to put it between 2 panes of glass and they're going to fuse that together. Based on the table at the right, which gas should they use at their insulator? Well, remember that high specific heats make good insulators. So when I look over here, this table, what I'm going to be looking for is the highest specific heat. The highest specific heat is nitrogen, so what I want to seal between my two types of glass, between my two glass panes, is going to be nitrogen, because it's going to be more efficient at insulating that window. Hope this was useful for you, and I'll see you tomorrow whenever we learn how to calculate specific heat.